using this option, and I'll put it at 3 comma. And you know I've placed it because it will appear in this side. Now we need a directrix. You can select line or segment because a directrix is an infinite line. So I'm just going to take segment and I will go like this. So that will be our directrix. Now hover over this ellipse thing, pick it, and because we are doing parabola for this demonstration, I will click parabola. So now we select the focus and directrix. And there we have it. We have a parabola. And you can move it so it becomes bigger or smaller. You can also invert it by making the point across the line. Okay, so we've learned how to do a parabola in GeoGebra that is upward or downward, but what about sideways? So we will mark the focus again at 3, 3. And this time, instead of the directrix being horizontal, you'll make it vertical. So I'll select this and this. Now, again, I will go to this option and select parabola, select the focus and directrix. So that is a sideways parabola, and you can again invert it. So now that you know about parabolas, I have prepared a couple of questions and a summer project. If you are listening to my presentation, I want you to ask yourself, what is a parabola? What is the focus and directrix? What is the most basic formula that can be used to describe it? What are the different types of parabolas? And what are some real-life examples? And for a summer project that you can do, I want you to design a structure of some sort that can help you in your daily life. Kind of like a simple machine. It includes some sort of parabolic form in that structure. Then explain how that shape of the parabola helps it do its job. Finally, I would like to thank Ashani sir and the whole of Shita for allowing me to have this opportunity to present about one of the most interesting topics in geometry. I would also like to thank my audience, and I hope you enjoyed it.
Very good, Aaron. I think you presented it very well, and I think your GeoGebra project was also very good. And you made it, and you made a good use of it. Okay.
Yeah.
Okay. So we can now move on to, and a great round of applause for Aaron. And now we can move on to Abhiram. Okay. Yeah. Atharv is doing it. Very good. Okay. So, Abhiram, are you ready?
Yeah, I'm ready.
Okay. So, yeah, you can tell about yourself and then you can start your project, your presentation. Okay. Okay.
Yeah, can you say?
Yes, yes, we can. We can.
Okay. So, good evening, everyone. My name is Abhiram. I study in 8th, 9th standard. Today, I like mathematics and also some problems which connect two parts of mathematics, like my topic, which is golden ratio in geometry. So, a golden ratio is one of the most famous and beautiful ratios all over mathematics, and geometry is one of the most, arguably, the most beautiful part of mathematics. So, let's see how they both are related. So, there is a statement here which I have written. Golden ratio doesn't only belong. Hello, can you hear me?
Yes, yes, we can hear you.
Okay. So, golden ratio doesn't only belong to Fibonacci number. That means, what do I mean by it? In Fibonacci numbers, there's a pattern that f of n is equals to f of n minus 2 plus f of n minus 1. And we know that the ratio of any two of these numbers is the same. What do I mean by this? It means f of n by f of n minus 1 is equals f of n minus 1 by f of n minus 2. So let's call it this ratio as delta. But we can substitute for f of n here in this equation, and we get our equation as f of n minus 1 plus f of n minus 2 whole divided by f of n minus 1 is equal f of n minus 1 divided by f of n minus 2, which is equal to the which is equal to delta. But after simplification, we get that 1 plus f of n minus 2 is divided by f of n minus 1 is equal to the delta. But we can observe something. This is nothing but the reciprocal of this. So it's nothing but 1 by delta, right? So we get that 1 plus 1 by delta is equal to delta. And solving this equation for delta, we get our famous golden ratio 1.618039 and so on. So also we can see that if there is a sequence where the nth term is the sum of the previous two terms, we get the golden ratio. Let's see an example. Let me take this sequence. So it's 2, 2, 4, 6, 10, 16, and so on. So let's see a magic in it. 2 by 2 is 1 normal, 4 by 2 is 2, 6 by 4. Now it's getting interesting update. 1.5. Then here 10 by 6, which is 1.6667, and 16. Like that, if you go down, we'll get 16 by 42, and like 16 by 42 is equal to 1.619, which is really close to the golden ratio. Then we have another sequence. So what I have did here in the golden ratio, we have 1, 1, 2, 3 like that, 1, 1 like that, 1, 1, 2, 3. But I have flipped 2 and 1, so we get this sequence. 1 by 2 is 0.5 again, 3 by 1, 3, 4 by 3. Here it gets close really fast, 1.3. Then 7 by 4, it gets even closer. And if you move down for 49 by 21, it's 16.120, which is really close. So like that, golden ratio is present all over all many of the sequences in the world. So let us dig into our main topic, which is golden ratio in geometry. So let's see how the golden ratio is present in equilateral triangle. So let us use a construction. Here ABC and FGH are two equilateral triangles such that the circumcircle of FGH is in circle of ABC, and in such a manner that F is on AH, H is on GB, and G is on FC. So we have this we get this relation that AF FH by AF is equal to GH by HB is equal to GF by GC, which is equal to our famous golden ratio. So let's see the proof of it. Without loss of generality, we may assume that the sides of the bigger triangle are 2 and of the smaller triangle are 1. And also let's assume that AF is equal to some number x, and let E be a midpoint of AB. Then naturally its value is 1, as AB is equal to 2. Then by power of point theorem, we get that AF into AH is equal to AE square. But AF is x and AH is x plus 1. So we get this equation x into x plus 1 is equals 1. So after simplification, we get this equation x square plus x minus 1 is equal to 0. And solving for x, or let me say AF, we get that AF is equal to square root of 5 minus 1 by 2. Then FH by AF is nothing but 1 by x, or 1 by root 5 minus 1 by 2, which is after simplification becomes 1 plus root 5 by 2, which is the famous golden ratio. Next, let's see example of golden ratio in a square. So let us take ABCD is a square with AM being the midpoint of AD, and let the capital R be the inradius of triangle BMC, and the small r being the inradius of CMD. Then we have this relation capital R divided by the smaller r is equals to our golden ratio. So let's see the proof, jump into the proof of it. So let's assume that AB, AD, and all with a square as a length, side length 2. Then by Pythagoras theorem, we can prove that BM is equal CM is equal to root 5, and we can also use the formula that area of a triangle is equal to its semi-perimeter times semi-perimeter times its in radius. Also, we can observe or prove that triangle BMC's area is twice of CMD. So then we get this relation, and 2 plus root 5 plus 2, which is the perimeter of BMC times capital R is equal to 2 times 3 plus root 5, which is a perimeter of CMD times R, from which we can simplify for R by R, which will we get as root 5 plus 3 divided by root 5 plus 1. And if we multiply the terms by their conjugate, we get this equation as R by R is equals to root 5 plus 3 into root 5 minus 1 by 4. And after furthermore simplification, we get that R by R is equal to our good old famous golden ratio 1 plus root 5 by 2. These are just some examples where the golden ratio can be found in geometry. There are many such examples. The question I have about this research project is, here we are taking the delta value of positive and get this golden ratio. What if we take the value as negative? Like I thought over it and I got that delta in the negative value is something called minus 0.6 something. So how does it? And also I want to research more about golden ratio. Like we know that cos 18 is some related to golden ratio and more stuff like that. Thank you. Thank you for listening.
Okay, Abhiram, a great round of applause for you too. Like your efforts are very good. You can see it in your project and your explanation too. Very good, Abhiram. Hello.
Yeah, your voice is breaking.
My voice is breaking. Okay. Okay. Is it breaking now too?
It's fine.
and it can be anything starting from 1. So pick any positive integer, and if it's an even number, we divide it by 2, and if it's an odd number, we multiply with 3. And like this, we will keep on generating the sequence. Like for example, if I take 5, then 5 is an odd number. So we do 5 into 3 plus 1, that is 16, which is an even number, which we divide by 2 and get 8, or again divide by 2, we get 4, and like this we continue. So this Collatz conjecture says that no matter what the integer is, we will always eventually reach 1, going on and on in an infinite loop. That is, whatever number we take, starting from 1 to infinity, or maybe if there is any limit to the numbers, if we take any number and we keep on doing this thing, we will always reach 1 for each and every number. So this is the statement of the Collatz conjecture. Now I am just if you can see this one, this is a pattern I have drawn. So if you see it properly, all the numbers 43, 65, 49, 37, 33, 25, 19, all these numbers, they eventually connect up at places and finally they will bound to reach 1. If you see this properly, it's like a tree, and these are all branches. The branches connect and connect, and eventually whatever number we take, we will get back to the ultimate 1. Who like the 3n plus 1 problem, because as we can see, whenever there is an odd number, we just keep multiplying it with 3 and then add 1, and then we also divide by 2. But this is sometimes called the 3n plus 1 problem. Secondly, it has got another name called the Ulam conjecture. It was named after Stanislaw Ulam. So Stanislaw Ulam, this is Stanislaw Ulam, another scientist. He also researched about this problem, but unfortunately Kutani. He was Australian American, scientist. He also researched about it, but not subject to multiple ascents and descents like hailstone in a cloud. If you had up, and then again 16 we divide it by 2, that is 8 divided by 4, so it's now going down. So 5 is just a simple example, but as you can see, in most of the cases the numbers just rise and fall and rise and fall and finally falls formation of hailstone which occurs in a cloud. That's why. So it is also called the hailstone sequence. Next is the mathematical form. I am coming to the mathematical form. As n by 2, that is, if we take the integer and we divide it by 2 when n is even number, and when it is odd number, we multiply with 3 and then add 1. So if it's n is odd. In modular functioning, this is what we call, modular functions. As you can see, if n mod 2, that is, if we divide by 2, the remainder is 0. So that means it is an even number. This is the modular, formulation. And 3n plus 1, if n gives 1, then it after mod 2. So as we know that any odd number, when we divide by 2, it always gives remainder 1. So that's why it's remainder 1. Here, I have shown a graph. It looks like some blood splattering or something like that, but it is actually a graph. So the thing is that this graph shows all numbers from 0 and to 9,000, and it all shows that all these numbers follow Collatz conjecture. This was a little bit earlier graph. The later research shows something else. I will come to it. But at first, till 9,000, all the numbers follow Collatz conjecture. That is, whenever we follow this sequence, whenever we follow these steps, it will all eventually lead down to 1. Maybe it will take many steps. It may take huge number of steps. Let me tell you, for example, if we take the number 27, 27 actually takes 111 steps to reach 1. So it's like, don't try this at home type. So okay, so 111 steps. So like this. So the number of steps which the integer takes to reach 1, this is what we call the stopping time. The stopping time is the number of steps after which an integer n reaches 1 in the Collatz sequence is known as its stopping time. The Collatz conjecture asserts that stopping time for every integer is finite. This is very important. For every integer, the process time or the stopping time is finite. So if we like keep going on and on and on for some big numbers, it will eventually reach 1, but in a finite time. It's not that it will take infinite time to reach 1. Okay, so this is the thing. So here I have given some small examples regarding the Collatz conjecture. So when we take n equals to 12, see, we divide by 2, we get 6. We divide by 2 again, we get 3. Then we follow the odd number sequence, we get 10, then 5, then 16, 8, 4, 2, 1. 17 if we take, we first 7 into 3 plus 1, that is 52. 52 when we divide by 2 gets 26, then 13. 13 is an odd number, so 13 into 3 plus 1 is 40, and 20, 10, 5, 16, 4, 8, 2, 1. And similarly, if we take the number 11, we also eventually get something. So, did you notice something? Did you notice something interesting here? All the numbers, I have shown 3 examples, but all those numbers which follow the Collatz sequence, they always end in the ordered pair 4, 2, 1.
I have one question. So that after, if you do the 3n plus 1 for the number 1 after that, will it just go repeating 4, 2, 1, 4, 2, 1, 4,
Yes,
2, 1, and so
of
on?
course. Yes, so that's an infinite loop. This is one of the major problem of the conjecture. That's why if we take 1 only, see, why is it said a conjecture? Because many scientists decided to check it with 1, but if we check with 1, we again eventually reach 1. We do not reach beyond 1, or we do not reach any negative numbers or less than 0 or something like that. So it keeps on going to 1. So it keeps on repeating in the 4, 2, 1 step. That's why I said that integers end with the ordered set 4, 2, and 1. See, if we take 1, then it comes to 4, then again 2, then 1. Again. So this one keeps repeating. So this is an infinite loop at the end, right?
3, the stopping time of 1, 3, because it takes 1 to 3 steps. 1, 2, 3, 4, 2, 1. So is
So that's why it's 3 steps to reach 1. So if we take 1 only, then also it reaches 1. But in most cases, we don't in Collatz conjecture. We try to take numbers beyond 1. That is like 2 or 3 or 4. But if we take 4 also, it also eventually reaches 1. So we have done visualization. So this is a properly, I don't know if you can see, because I couldn't fit both of them properly. So it's a video. I am just starting it. You check it once and tell me. So it's starting with 1, then we get 2, then get 4, then get 8. Now, if you can see, all these numbers, this is a branching of the numbers. See, every numbers you can see when the graph ends, it eventually reaches these 4 steps, that is 16, 8, 4, 1, 4, 2, 1. So these are many numbers are given in this circle and they all reach down to 1 by somehow. See, if you follow 6144, then we follow this line, and then we go here. It's like a jigsaw puzzle, right? When we used to do those pathway things that bring the cat out of those puzzle maze box. It's something like that. So if whenever you start, it will eventually reach this last 3 squares. Although they have given 1, 2, 4, 8, and 16, but we prefer 4, 2, and 1. This is because one of the students who said that we take 1, we reach 4 and 2, 1. So that's why we take the 4 to 1 as the ordered set and not 8 and 16 also. So this is the circle. If you want to see it, I can show it another one. And here I have 0, 2, 2 to the power 68. That's a I'm not going back, I'm just telling you. If we are taking the number 11, so 11 into 3 plus 1 is 34. By 34 by 2, we get 17. So when we take 11 and we get the numbers we are getting in the 11 sequence. What are the numbers we are getting in the 11 sequence? We are getting 34, we are then getting 17, we are getting 52, 26, 13. So these numbers which are already in the 11 sequence, that is 34, 52, 26, these numbers are also part of the Collatz conjecture. This is something, if I try to explain you, that is, the thing is that, for example, in a sequence, the numbers which are already in a sequence for any integer, those numbers are also part of the Collatz conjecture. So thing is that if you want to show an example to someone, so if we tell that 11 is a Collatz conjecture, 11 follows Collatz conjecture, then 34, 26, 17, 13, they also follow Collatz conjecture because they will also eventually lead down to 1. That's why you can say, although this circle does not show all numbers, it's not possible to show all numbers, but they have shown some minor some major numbers which eventually like twist and turn to finally reach down to the last 4 steps. And this graph, this is a very hazy graph. I couldn't zoom it much more, but it shows all the numbers from 0 to 2 to the power 68. That is almost equivalent to 2.58 into 10 to the power 20. That's a huge number actually. Okay, so let me continue. Okay, so supporting arguments and proofs. So see, if there is a conjecture or if there is a mathematical statement, this is just a mathematical statement, there ought to be proofs because many scientists try to prove it. So here we have some proofs regarding the Collatz conjecture. First of all is the computer evidence. In 2020, the conjecture has been checked for all values up to 2.95 into 10 to the power 20. That's just what I said before. 2.95 into 10 to the power 20 is also equals 2 to the power 68. And all the values end in the repeating cycle 4 to 1. Of course, this computer is not our computer which we use, they are supercomputers. In supercomputers, it were checked up to such a big number, that is 2.95 into 10 to the power 20. But all the values ended in the repeating cycle 4 to 1, if we follow that Collatz sequence. However, computer evidence is not enough, as counter examples might be found for more larger numbers. But see,
So there might be one example which does not tend 4 to 1, 4 to 1, and so on. It might go 369, 369, or it may even not repeat.
no, the thing is that counter examples, what I say is that all the numbers up to 2.95 into 10 to the power 20, that is 2 to the power 68, they have been proven for Collatz conjecture. But if we go for bigger numbers, see, a supercomputer has also some limit. But we don't know what is the end of numbers. It may go up to infinity. This 10 to the power 20 may also be 10 to the power 2000. So if we go like this very, very, very big numbers, astronomical numbers, the type of that, then we may find some counter examples. But till now, no counter examples have been found yet. consider only the odd numbers in the sequence, then each odd number is on average 3/4 of the previous one. So this is an interesting one. It says in the hailstone sequence, let's consider, we only consider the odd numbers, not the even numbers. Let's say that the even numbers are type of silent. So if we have only the odd numbers, then each odd number, that is the succeeding odd number, is on average 3/4 of the previous odd number. It is just an average. Okay. So this probabilistic argument sometimes shows that all the numbers are bound to decrease in the long run. So like for example, if we have a number, any number, say x, then the next odd number will be 3x by 4, that is 75%, that is 0.75x. And again, after the next number after that, there will also be 75% of 0.75x. So it goes on decreasing, right? So finally, after all, the numbers are bound to decrease. This was a heuristic argument, although this never was a proof, because we are considering the fact that we are only taking the odd numbers, not the even numbers. But then also this proof was once, an argument was drawn, but this was not actually valid. Finally, Terence Tao. He is an Australian-American mathematician. You can see the picture here. He is Terence Tao. So in 2019, Terence Tao, an Australian-American mathematician, tried to solve the Collatz sequence using the concept of logarithmic density and partial differential equation. Terence Tao was a brilliant student, a genius actually. So he tried to solve the Collatz conjecture using the logarithmic density and partial equation. His results are still now by far considered the most significant proof, as they prove that
Hello.
99%. Hello.
Sayak, sorry to interrupt you. You were having a good presentation, but the problem is that we don't have much time. So
Okay, it's just going to end. Just
Okay.
1 minute. It's almost at the end. So Terence Tao. Okay, so let me be a little bit fast. So Terence Tao tried to solve this concept using logarithm.
ये पूरा Hello, Sayak. We cannot hear you.
You're frozen.
Yeah. Actually, I think now I don't know. Am I audible to all of you?
Yeah.
Yes.
Okay, so Shayak is not audible to us. Okay, but he did a really good presentation, and I must um, appreciate Atharv as well for participating in his project. Okay, so I think whenever one finds a question, yeah, then they must find an answer to that.
And one question though.
Yeah, tell us.
I'm not in the live stream. Can I present again?
Yeah, you can do it. Okay, so let's do one thing. Let's take Anshuman's project first, and then I think you can do it too. Okay.
Thank you.
Okay. So okay. So Anshuman, I'm sharing the screen. I'm sharing the screen for you, Anshuman. Okay, but I think it will be quite difficult to do it that way. Let's start. And just tell me that when I should change the slide. Okay. Okay. Mm. Okay. Can everyone see it?
Yeah.
Okay. So tell us, Anshuman, that what about yourself and what is the project about. Okay. So you can start and tell me when to shift.
So, I'm actually going to do this project about Bell's equation and how you can solve it using various methods like continuous fractions and other methods. So you can start the slideshow.
Okay. So are you all able to see it?
No, I don't think the slide. We started the slideshow.
Yeah, it is not in present.
Yeah.
It's not in present mode. Okay. Um.
Ma'am, someone is wanting to join the call.
Someone is wanting to join the call. Let me see. Okay. Okay. It's Sayak only. Okay, Anshuman, you can do one thing. You can present it from your side. Okay. I think it's not
I,
happening from my side.
I can't
So
present it from here.
can you join via laptop and join it, please?
I don't have a.
Okay. Okay. So let
You
me check once. Let Atharv present it once. Okay.
Okay.
Let me see. Okay, Atharv, can you start?
Yes, I can.
Okay,
But
please do.
just one moment, I'll then present for water and car.
Hello guys, I hope you all are enjoying this live session out here. How's the whole thing going on, Simran? How is the whole thing going on, guys? Abhiram, Aaron,
It's going
Alka,
fine, but
Panchak, how is the presentation going on? Very good, lovely. I hope you're enjoying it, guys.
Yes, sir, very much.
Okay, okay. So, what is the name of this lot of the strings?
hello.
Yeah, yeah. Hello. Hi, Shan. Hi. Your presentation is done. Okay, lovely.
Okay. So Anshuman is not able to present because he's on his tablet and his presentation is with us.
Sir, you're presenting? Where's your presentation?
It's your.
Yeah. And Atharv is presenting once more.
A very good evening to you all.
My name is Atharv Nadkarni. I am studying in class 2. I just turned 8 years old last week. I live in Goa. I took a liking for maths when I was 3 years old. My other two favorite subjects are computers and music. I have developed my own website using HTML and CSS when I was 5 years old. I also blog about maths on the website, and I have a YouTube channel where I made videos on maths. My topic for today is Pythagorean theorem and its triplets. Now let us see who is Pythagoras. Pythagoras was born in Samos, Greece in 570 BCE. He died in 495 BCE. The 6th century BC philosopher, thinker, and founder of Pythagoreanism. Pythagoras was credited with the Pythagorean theorem, Pythagorean theory, and Platonic solids. What is the Pythagoras theorem? A right-angled triangle has two sides A and B and hypotenuse C. Pythagoras theorem states that in a right-angled triangle, the square of the hypotenuse side is equal to the sum of the squares of the two other sides. In algebraic language, it is written as a square plus b square is equal to c square. He formulated the theorem stating a square plus b square is equal to c square for only specific values of a, b, and c. Now let us look at the right-angled triangle in GeoGebra. This is a right-angled triangle. The sides are labeled A, B, and C. The reason it is called a right-angled triangle is because the angle between the line A is exactly 90 degrees. Now to my presentation. Pythagoras theorem does not vote for all the values of A, B, and C. The values for which it does vote to are called Pythagorean triplets.
Yeah, I think
What
you can
are
start the presentation.
Pythagorean triplets consists of three
They
positive
will join.
integers
They
A,
will
B, and
join.
C.
They will
Such
join
that
on
A
Google
square
Meet.
plus B square is equal to C square. This
So
theorem
calendar
has
में
over
जाओ,
200 proofs.
calendar में
But we
जाओ,
are most
चिंतार्य भट्ट
interested
का,
in today
and
in
you
how
will
to
get the
generate
link
the values of
from
A,
there.
B, and C. Now let us
Okay.
look at two
हाँ,
groups of
I will
three
complete
positive
this.
integers.
Okay, they are waiting for
One
you.
which does not work and the other which does in a Pythagorean theorem. For example, let A equal to 3, B equal to 7, and C equal to 9. That gives you 3 square plus 7 square is equal to 9 square. You put it in the Pythagorean theorem, and that becomes 9 plus 49 is equal to 81. No! As you can see, the Pythagorean theorem does not work here. Another one. Let A equal to 7, B equal to 24, and C equal to 25. Due to the Pythagorean theorem, we get 7 square plus 24 square is equal to 25 square, which gives you 49 plus 576 is equal to 625. Yes! As you can see, Pythagoras theorem works here. Now let us look at Euclid's formula to generate Pythagoras triplets. Euclid's formula will generate Pythagorean triples given an arbitrary pair of positive integers m and n with m greater than n greater than 0. A primitive Pythagorean triple additionally requires m and n have opposite parity. That is, if one is odd, the other must be even. M and n are co-prime. That is, there is no common integer factors greater than 1. is equal to m square minus n square. B is equal to 2mn and C is equal to m square plus n square. With this information, let us look at two examples. Example 1. Let m equal to 9 and n equal to 6. A is equal to 45. A is equal to 9 square minus 6 square. A is equal to 81 minus 36. A is equal to 45. B is equal to 2 into 9 into 6. B is equal to 18 into 6. B is equal to 108. C is equal to 9 square plus 6 square. C is equal to 81 plus 36. C is equal to 117. Now let us see if this is a valid. A square plus B square is equal to C square. 45 square plus 108 square is equal to 117 square because 2025 plus 11,664 is equal to 13,689. So here we have used Euclid's formula to generate Pythagorean triplets. Another example. Example 2. Let m equal to 12 and n equal to 7. A will be equal to 12 square minus 7 square. A is equal to 144 minus 49. A is equal to 95. B is equal to 2 into 12 into 7. B is equal to 24 into 7. B is equal to 168. C is equal to 12 square plus 7 square. C is equal to 144 plus 49. C is equal to 193. Now let us see if this is a triplet valid. 95 square plus 168 square is 193 square because 9,025 plus 28,224 is 37,249. So here we have used Euclid's formula to generate another set of Pythagorean triplets. You need to note that there are other formulas that can generate Pythagorean triplets like Plato's or Fibonacci. But today we are only going to look at Euclid. Thank you.
Very well done, Atharv. Very good.
Thank you.
Yeah, very good. I think you have used your algebra very well, and I think I can try with presenting Anshuman's project once more. Okay, let's see if it happens properly. So I am presenting my screen once again. Let's see if I can do it.
Was my presentation? It just got disconnected at the last moment.
Who?
Ma'am, Shayok.
Sayak is here. Sayak is telling that you got disconnected.
So was my presentation okay?
Yes, of course it was okay. Actually, we could not give you more time, but I must tell that you presented very well, Sayak, and you explained Atharv as well. That was the biggest. I think that was the biggest thing that you did.
Sorry, what I did?
You explained Atharv's questions as well. You answered to Atharv's question. That was a very good discussion.
Okay, thank you, ma'am. I just tried. It was a bit long, but my net just suddenly got disconnected. Thanks God it didn't get disconnected while I was explaining.
Yeah, it didn't get. So let me see if I can do it. Can you see what I have shared?
Yeah.
Yeah, we can.
Yes.
Okay. So can you see the presentation now?
Yes.
Okay. So Anshuman, can you start presenting?
Yeah. So we're going to talk about Bell's equation. Can you go next?
Okay.
One second.
Hello. Hello.
Yes.
Anshuman, please continue.
Yes. So this is about what is Bell's equation. So the equation u squared minus dv squared is equal to 1 with d a positive integer that is not a perfect square is called a Bell's equation. D should not be a perfect square. That's because if D was a perfect square, then U will be 1 and D will be 0. So that's not actually a good solution to think of. So this was known from the ancient times in connection with the famous cattle problem of Archimedes, and it was brought to the attention of mathematicians of modern times by Fermat in 1597. Euler, who also studied it, he attributed the equation to Bell. That's why it's called as Bell's equation. And the first complete solution was given by Lagrange in 1766. Next.
Okay.
Again, yeah. So this is a method of solving the Bell's equation by using continued fraction. So first you have to consider the continued fraction. Root d is equal to a1 plus 1 by a2 plus 1 by a3 and so on. Then the sequence a1 plus a2, a1, a2, a3 is periodic starting with the second.
Hello. Hello. Anshuman, can you hear me?
He is frozen.
I think he is facing some connectivity issue. Okay. Let's stop sharing his screen then. He's not here. Hello?
Yeah. He left again.
Hello, Anshuman. Can you hear us?
Yes.
Okay. So will you continue your presentation? Just a second. Let me share again.
Yeah.
Yes, continue, Anshuman.
Yeah, I read this. So you have to go to the next slide. Yes. If you want to show that the continued fraction method does not give any solution, you have to use that D is perfect square. So if you can also say that if there are no other solutions, right? And if the continued fraction method it doesn't give any solution, so it will mean that obviously like for that B there's no solution. And if there is the solution. So you can prove that it actually gives all the solutions. So let's start by showing that u and v and root d actually are lesser than u plus v root d. It is lesser than un plus 1 plus vn plus 1 root d. Now let alpha plus beta root d is equal to u plus v root d upon u1 plus vn root d. And since u1 plus vn root d is u1 plus v1 root d to the power n, 1 is greater than alpha plus beta root d, which is greater than which is u1 plus vn1 plus 1 root d upon u1 plus vn root d. Now since u1 plus 1 plus vn plus 1 root d is u1 plus v1 root d to the whole power n plus 1, then u1 plus vn root d is u1 plus v1 to the whole power n, so it will just simplify v1 plus v1 root. Now note that a alpha plus beta root d is u plus v root d times un minus root d by factorizing it, and you can combine the terms to get u minus v and d plus v un minus v and root d. So alpha and beta integers. Now since alpha plus beta root d is greater than 1, and 1 is obviously greater than 1 by alpha plus beta root d, since alpha plus beta root d is greater than 1. So this will imply that alpha minus beta root d is greater than 0. So alpha is greater than beta root d is greater than 0. So alpha and beta are in fact positive numbers. Now by taking conjugates, we'll obtain that alpha minus beta root d is u minus v root d upon u minus v and root d. Now if you multiply this by alpha plus beta root d, so that imply that alpha and beta is solution, whether that's wrong, since alpha and beta are obviously lesser than u1 and v1, but then u1 and v1 has to be the least solution. So that will contradict the minimality of u1 and v1. So all the solutions are given by this. And if it doesn't give a solution and necessarily need a now this is another identity of the solutions to the Bell equation, which is Parabola. Now since x1 minus n y1 square times x2 minus n y2 square is equal to x1 x2 plus n y2 square minus n times x1 y2 plus x2 y1 square. So using this identity, Brahmagupta was able to compose a couple of triples such as x1 y1 z1 and let's say x2 y2 and k2. These are the solutions to x square minus n y square is equal to k. Now we can use this to get other solutions such as x1 x2 plus n y1 y2 and x1 y2 plus x2 y1 and k1 k. So this can create infinite solutions to the Bell equation. Now let's try to prove the Brahmagupta right. So a square plus b square is c square plus b square. So here we are assuming n to be 1. And if it works for n is equal to 1, so you can prove it for any power for n, like for example, you can take n is equal to 2 and so on. Now for this n is equal to 1, if you open the brackets, you'll get a square, c square plus a square d square. So b square c square plus b square d square is equal to a. Now to complete the square, so you'll add and subtract 2abcd. So it'll be ad plus minus bc square and ad plus minus cd square. Next. And this is Bhaskara 2's Chakravala method. So this method starts with choosing integers a, b, k which satisfy a square minus nb square is equal to k square. So you get the solutions. So the triangle is going to be m1 m square minus m1 and m square minus x. And you can use this to get the triple am plus nb, a plus bm and k times m square minus n. And now this can lead for the solutions like am plus nd by k, a plus bm by k, and the m square minus n by k. Next. Yeah, so these are a few solutions of the Bell's equation. So you can notice here that there aren't solutions for all the perfect squares like 1, 9, 16, and so on. So we can use this method for even big numbers like 109. Get solutions which are very huge. Next slide. Thank you.
Okay. So, well done, Anshuman. There was some voice. I think the voice was not clear that much, but it was very nice presentation and very nice animations too. So, all of you, very well done. Okay. So, we wish that you do this good in your individual round as well. Okay. And I hope you enjoyed the session. Okay. Hello.
Okay.
Okay. So,
Yeah.
bye everyone.
Bye.
Bye.
Yeah.